Hello, hello, hello everybody, and welcome back. We are starting part B in this video on our 2018 Canadian Senior paper. So we're going through B1 and then B2, so we'll just be doing B1 in this video. We've got 3 questions to go through. And these are the written questions, so you do need to justify everything you say, clear sentences, clear pictures, showing your calculation. That's exactly what we want to do. So for question number 1 here, Alexandra draws a letter A, which stands on the x-axis. Okay, that doesn't quite look like an A, but who knows? We got 4 parts here. A part. The left side of the letter A lies along the line with equation y equals 3x plus 6. What is the x-intercept of the line? Okay, so we want to know, where does it hit the x-axis? There's a couple ways you can do this. Right now it's in what is called y equals mx plus b form. This is a very common form because it highlights the the y-intercept 6. But there's another form that's quite nice that I always try and plug when I can, and that's the y equals x or mx minus a form, and a here is the x-intercept. So if we were to factor out a 3 from both 3x and 6, we'd get x plus 2. Now we do need x minus a. So writing the plus as minus minus, we could see that the x-intercept is going to be at minus 2. This is, of course, not the only way to do it, but it's a nice way. Where is the x-intercept? Well, it's found when y is equal to 0. So instead, you can just take this equation, bring the 6 over to the other side, and divide by 3 on both sides. So either way, we can get negative 2 as the x-intercept. And either one is fine. They both involve about the same amount of calculation. So there's nothing you really need to worry about there. All right, B part. The right side of the letter A lies along the line L2, the division here, and the letter is symmetric about the x-axis. What is the equation of line L2? Okay. So it's symmetric about the x-axis. Well, how are we going to get symmetry? Well, think about it this way. We know the slope of this line. What could we maybe guess for the slope for L2? So this 3 over here tells me if I go 1 over, I'll go up by 3. Symmetrically, what we want to do is if we go down by 3, we should go 1 over. And that's going to tell me that I'll get a slightly different slope. My rise will be negative 3 and my run will be 1, as opposed to rise of positive 3 and a run of 1. So this is sort of a general rule that if you got a slope of m and you reflect in the y-axis, your new slope will be minus m. Okay, this is it's a less known rule, but it's similar to how if I've got a line and I've got a perpendicular, and I know the slope of 1 is m, the slope of the perpendicular is negative 1 over m. These are both good things to know. And you can explain the rise over run stuff if you want to. I think it's fine to say the slope of line 1 is 3. So symmetrically, or by symmetry, we see the slope of L2 must be negative 3. Okay? What else do we need to get the equation of L2? Because that's what we're asked for. What's the equation of L2? Well, the lines meet at the y-axis. So we could say they have the same y-intercept, and that was 6, which I sort of remarked in part A, although we were finding the x-intercept there, but it's 6, so L2 has equation y equals negative 3x plus 6. There we go. All right, so that's B part taken care of. C, what do we got for C? Determine the area of the triangle formed by the x-axis and the left and right sides of the letter A. So basically want the area in here. Okay, well, just do base times height, or 1/2 base times height. So L2 has x-intercept. Why am I finding the x-intercept? When I draw the picture, you'll see in a moment, but while I got space, I'm going to do this. It's got x-intercept, well, if we factor out the -3, we'll get 2. So what have we got? Well, if we draw our picture, -2, 0 here. This is by part A. 0, 6, which I noted it in B part. We didn't prove it in B part. I just pointed it out. And then we just showed that 2, 0 is the x-intercept of the other line. There's L2 and L1. Okay, so the base is 2 minus -2. You can just say 4. And the height is 6. So the area of the triangle is 1/2 base times height, 1/2 of 24. This is 12. Okay. So there we go. Not really too much to do, but we did want to point out where we're getting this x-intercept from so that we can show where we calculated the base. And then D part, so the last little bit for B1. Alexandra completes the letter A by adding to figure 1. She draws the horizontal part of the letter A along the line y equals C, so some nice horizontal line. The area of the shaded region inside the letter A and above the line with equation y equals C is 4/9 of the area, the total area of the region that we just calculated. We want to know what's the value of C. Okay. Well, I think there are probably a couple ways we could go about doing this. There's sort of, I would say, the slower way. So I'm just going to build off my previous picture. We can include this y equals C. We could do, this area. We know the area is 4/9 of 12. And that'll be 16/3 when all is said and done. Okay, so we know it should be 16/3. Now, what's the height here? Well, it was 6, but now we've gone up by C, so the new height is 6 minus C. What about the new base? Well, we could find out where y equals C intersects these two lines. Thanks to A and B, we know the equations for these lines. So C equals 3x plus 6, and C equals minus 3x plus 6. Okay, we should get nice symmetry here. So we'll get C minus 6 divided by 3, and C minus 6 divided by -3 for our x values. So the new base, this distance here, well, we're going from C minus 6/3 C all the way over to C minus 6/3 C. I do have the order of these correct. C is clearly bigger than 6, so C is clearly less than 6, so C minus 6 is negative, so dividing it by -3 would give me a positive x value. So it'll be C minus 6/3 minus C minus 6/3. Okay. C minus 6/3 minus C minus 6/3. And that'll be 12 minus 2C/3. Okay. And so the area, which we know should be 16/3, is 1/2 base times height. Multiply by 3, multiply by 2, you're going to get 32 is equal to, take out a factor of 2 here, 6 minus C squared. Divide by 2, we can take 16 is 6 minus C squared. So 6 minus C is 4 or minus 4. And rearranging, we can say C is 2 or 10. That's too big, so C is 2, and we were just asked what C is, right? Determine the value of C? Yeah, 2. So that's one way to do it. You'll notice that we had to use some fractions, we had to calculate a new base and everything. Okay. It's fine if that's your go-to. I mean, it didn't take that much trouble, it wasn't that many calculations, nothing particularly weird. Okay. But let me show you another way to do the question that I think is a little faster. At least I think it'll be a little faster. I haven't actually tried this method, but it should be faster. So this nice little horizontal line y equals c. We can see pretty quickly, because it's parallel to the x-axis, that we're going to get some similar triangles. Okay, so if we gave these things names, you might call this A, B, C, D, and E, you can see that A, B, C is similar without too much difficulty to A, D, E. Okay? Now, we could start talking about similar triangles and a whole bunch of other stuff, but one thing I want to point out with similar triangles is that if you have a triangle and you take all of its lengths and scale them up by a factor of r, so if this was A, B, C, and now we've got RA, RB, RC, the area, if we call the old area capital A, well, if we call the old area X, the new area will not be Rx, as some people sometimes think, but multiplying all the lengths by r, including things like height and in radius, and every length of the old triangle has been sort of multiplied by r. The area, two-dimensional stuff, will all increase by a factor of r squared. And this isn't just true for relationships between similar two-dimensional shapes. It also works in 3 dimensions. If I take a cube and I sort of double all the lengths, I will quadruple the surface area, but I will increase by a factor of 8, 2 to the 3, the volume. Okay? So how does this help? Well, we know that the area of ABC is 4/9 the area of ADE. But they're similar. So AC scales up by a factor of, let's say, R to AE. We just don't know what this R is. But R squared should be 4/9, and if you square root it, you can see R is going to be 2/3. Now, as I said, it's not just these outside side lengths, it's all lengths that have to do with this triangle are scaled up this way. So, the old height was 6. The new height should be 2/3 of that. 2/3 of 6, well, that's 12/3. That's going to be 4, and this is a faster way. I know it's a little slower because I'm having to explain it in case this is your first time seeing something like this, but this is a faster way to get the 4 here, and then, well, that's just 6 minus C. So you get C is 2 there. Okay? You'd have to clean this up, and you'd have to say, well, by similar triangles, you'd probably have to introduce this R. But I would say if you didn't have to stop and explain it to somebody, it can be a faster way to do it, and it's also a nice connection to make. Sure, we can do the question the way we did. We can do D part the way we did. But knowing about this other way can be helpful, because in the future, on another similar question, maybe we won't have the equations to work with, and we will have to just rely on our knowledge of how similar triangles work. And it's not just similar triangles, it's any sort of similar two-dimensional shape. Scale all the lengths up by a constant factor, you will scale the area by that factor squared, and volume by that factor cubed. And if you wanted to go into the 4th dimension, the hypervolume by r to the 4. Okay? So it's a nice, useful fact, and it can certainly help us. And we've gotten C equals 2 in 2 different ways. So I think that's an excellent place to end our question B1. Up next, we're going to be taking a look at B2. So feel free to give it a try before joining me for that in the following video. Until then, take care and have a wonderful day.